Okay, so first, I want to thank everyone who has joined us. This is the first time that I am doing a dev talk or anything similar to it. So I'm very excited, and I hope that this will be useful for everyone who's participating. Like Amina said, the day after tomorrow, I'm going to be 1 year working exactly with Authority Partners. And it has been very exciting doing what I love the most, and stepping out of my comfort zone, learning new things, new technologies. And I have nothing but gratitude for this opportunity that I've been given. Um, so let's jump right in to our agenda. Today, I will be talking about what is intelligent query processing in SQL Server 2019. This is something new. It is built upon adaptive query processing, which was first introduced in SQL Server 2017. And we will also be seeing the different features that it brings, like table variable deferred compilation, batch mode on row store, T-SQL scalar user-defined functions inlining, and approximate query processing. So jumping right in, right? What is intelligent query processing? So IQP is a family of features that includes enhancements with broad impact that improve the performance of existing workloads with minimal implementation effort to adopt. So the key word here is minimal implementation effort to adopt. Um, we normally prioritize scenarios where a large population of customers are impacted. So Microsoft, and this is going to be kind of funny, after the introduction of Azure SQL database, they had to do something because once databases started to be hosted on Microsoft servers, they found out that there is horrible code out there, and this code was causing a lot of issues on the Microsoft side. So they said, "Oh my God, we have to do something because the perception is that our service is not good enough." And clients are saying that things are slow, but it's not because of the infrastructure, it's because of the bad queries. So they said, well, the only way we can solve this is by improving the query engine. Um, so they started to look at different clients and and see and seeing what can be improved. So they started with SQL Server 2017 and they introduced adaptive query processing. Here's a small graph, right, that shows us everything that is inside of intelligent query processing. So adaptive query processing, like I mentioned, started in SQL Server 2017. Basically, what this does is that it adapts. Before SQL Server 2017, when you executed a query, the plan for that query execution would be cached, and every other execution that came after that would use that plan that is cached. Now, if this plan that is cached is not a good plan, then everyone is going to suffer from this bad plan that's in the cache. So what Microsoft did is introduce this new feature that it adapts. It learns from previous executions and changes the plans that are already cached. Inside of adaptive query processing, we also have interleaf execution, and we have memory graph feedback. Batch mode specifically, the ones that are in blue were introduced in 2017. The boxes that are in green are all new in SQL Server 2019, and these are the ones that we're going to be focusing on. So I want to say something here to my dev colleagues. I know that most of you guys are probably developers, and I want to talk out of the bottom of my heart. I know that because of the way that our industry works, we have to deliver code fast. Um, and sometimes we rely on things like ORMs, which are great. Trust me, I love ORMs. They help us focus on a code first approach and gets us to complete our dev projects faster. So I totally understand that. But I want to encourage you to learn, especially if you develop applications that interact with OLTP databases that are highly transactionable, I recommend that you learn the features of the underlying relational database management system that you're using. In this case, we're talking about SQL Server. So you should know how queries run underneath the hood. If you can learn in a deep manner how query processing works, execution plans, cardinality estimator, cost estimation, etc., you're going to be a better software developer. You're going to be able to take advantage of what your RDMS has to offer. So I encourage you to really learn, which will make you a better developer in the long run. So getting back to it, execution plans. We're going to be talking about that a lot in this session because this is the basis of what query processing is. There are two phases in SQL Server when you run a query. First, you have the query optimization, which is where the query text is parsed. So basically, SQL takes your query and says, okay, it's correctly formatted. Then the cardinality estimator estimates the number of rows that it's going to flow through each operator. Basically, what SQL is doing here is saying, okay, so you want to select data from this table. So how many rows is that approximately? So that he can prepare a plan that will be better suited for the amount of rows that are going to be used. So then based on that, it calculates the cost of the query of that plan. And the cheapest plan is going to be selected to be cached for being reused by queries with the same text. So after that, the second phase is that the actual query execution happens, which uses the cached plan. Then it acquires memory grant based on what was estimated in the query optimization. And then finally, the query starts executing. So why is this important? Why are we talking about this? Because if we get the cost incorrect, we're going to have slow query response time due to inefficient plans. We're going to have excessive resource utilization. We're going to have high CPU, high memory consumption, high I/O. We're going to have spills to disk. This is when the plan does not require enough memory for the operation. So then he has to go to tempdb to complete its process. And remember, always, memory is going to be faster than disk. It's also going to reduce our throughput and concurrency because if we have a lot of requests that are asking for large memory grants and we assume that we don't need that large memory grant that we asked for, it's not going to give it back. SQL is a memory hog. He does not like to share. So he's going to take the memory he said that he needed, and even if he doesn't need it, he's not going to give it back. So if you have a lot of concurrency and you have a lot of people asking for a lot of memory, you're going to have a lot of contention there. And finally, T-SQL refactoring is something that costs money and time, because if you have issues like this that with slow performing queries, you're going to need someone to take a look at this, and we all know that time is money. So what does intelligent query processing offer us to solve these issues? We'll begin first with adaptive query processing. We mentioned before that it was first introduced in 2017. So intelligent query processing is built upon that. It takes that adaptive process that was thought of in SQL 2017 so that we don't have static plans in the cache, and they are able to adapt to different scenarios. So now we don't only want to adapt, we want to be intelligent about what we do. Hence the name Microsoft chose for intelligent query processing. So adaptive joins, what this is it dynamically selects a join type during runtime. This allows execution time selection of either a nested loop or a hard hash join algorithm. We should all know that SQL Server has 4 types of join operations. There are nested loop joins, merge joins, hash joins, and the new adaptive joins introduced in 2017. So if one join input is smaller than 10 rows and the other join input is fairly large and it's indexed on its join columns, and the index, then what the query optimizer does is it chooses a nested loop join for this one because it's going to be faster to perform the join and require the least I/O for fewest comparisons because it's not a large data set. Now, if it's a large join with a lot of data being compared, then SQL is going to choose a hash join, which can efficiently process large, unsorted, non-index inputs. So these are useful for intermediate results in complex queries. Now, after 2017, with adaptive joins, SQL now can choose one or the other. It changes in the plan. So you can have the same plan for the same queries, and depending on the amount of data, he can change from a hash join to a nested loop join. So what happens is when the plan is being created, it waits until it scans the first inputs. And then he says, okay, so this is not a lot of data, so I'll go with a nested loop join. And this is important because we mentioned about the memory grant, and according to the joins that it chooses, the memory grant will vary. So apart from that, we have interleaved executions. And what this is that when we have executions of multi-statement table value functions, and we use a fixed guess for the cardinality estimate, if the actual number of rows is much higher than what we guessed, the performance downstream is going to suffer. So with adaptive query processing, this feature uses the actual cardinality of the multi-statement table value function encountered on first compilation. So after the first execution, he's going to benefit from using that same plan over and over again. So let's see an example of that real quick. Let me bring up my... Okay, here we go. So for testing purposes for this talk, I am using SQL Server 2019 Developer Edition. I just wanted to mention that all of these things apply also to Azure SQL Database. And SQL Developer has been available free since SQL Server 2016. So you can go and get that from the Microsoft website for free for your own dev environments. And it has all the features as the Enterprise Edition. So let's see what adaptive joins look like. So as we mentioned in our opening statement, Microsoft thought of a way that it can implement these features with the least interaction from the clients. So all you need to do to be able to take advantage of these new features is set the compatibility level of your database to 2019, which is 150. For adaptive join, you can use 140, which is SQL 2017, okay? So right now, I'm going to set my database to the compatibility level 150. And now I'm going to clear my, my proc cache. You can do it this way, the traditional way, or you can use this new alter database scope configuration to clear the preceded cache. Sorry. All right, so now I'm going to use my database. And I am going to run with live query statistics, this small query. For testing purposes, we are also using smaller data sets because we don't want to stand here and run a query that takes 10, 20 minutes to run. But the concept is the same. So what we need to learn is how to use this in our real world scenarios. So we have this query that we're joining an order table with a dimension table. And we have a where we have a predicate where we're saying that the quantity needs to be equal to 360. So when we run this, notice that it brings 206 rows. And in our live query statistics, we see that there are 3 different inputs. So, and we have an adaptive join here. If we hover over the operation, notice that it says that estimated join type is a hash join. So it's saying, hey, I'm doing over 200 rows. So I'm going to do a hash join to be more effective. So if you hover over the different operations here, you'll notice that here, the actual number of rows was 206. If you go to the next one, you have the actual number of rows, which is 2. And if you go to the third one, it says 0 because he used the hash. So he used these 2. Now, if we run for this, let me clear everything once again. If we run the same query, but we change the where, now notice that we have only 5 records which we're working with. So now he's saying, okay, this is not so big, so I'll use a nested loop join. Notice that the plan is very identical, except now that we have here the actual number of rows is 5, and we have here 0 because we didn't use the hash join with this operator, but we did use this one. So now we have 5 actual number of rows that were read. So this is basically what adaptive join does. It adapts according to the workload size of the query. And all we need to do to be able to take advantage of this is set our compatibility level to 150. Okay, so let's continue on with our presentation. And we are going to be seeing an example later on about memory graph feedback. Okay, so next we have table variable deferred compilation. And before SQL Server 2019, the query optimizer would assume that a table variable has 1 row. And I think that this might be one of the mysteries of the universe that is still not resolved to today. Why would you assume that you are going to use 1 row for every time you use a table variable? Come on, Microsoft. But okay, that's not the point. So obviously, this would result in a less than optimal query plan in most situations, because most situations we're not just working with 1 row. So the 2019 edition is going to use the actual number of rows in table variable to create a plan, just like temporary table does, right? He's not going to assume that it's going to be 1, but at the moment of compilation, he's going to wait to see what the actual workload is before he says, okay, this is the plan that I want to create. So let's jump right back into our scenario here, and let's do a small test. 1 second. Okay, so for this example, I'm going to be using the Stack Overflow database. These databases are available online. They're free for testing purposes. Again, I'm going to clear my procedure cache. All right, and I am going to set the compatibility level to 140, which is 2017, so that we see what happens when we run a query with a table variable. All right, so we have a very simple, trying to keep it simple, query where we are going to include our actual execution plan, and we are going to introduce 1 row into a table variable, and we're going to select from it. So when we do that, we have 1 row. We have here our execution plan, and he says, well, I estimate that I'm going to read 1 row, and I actually read 1 row. So we don't have any issues. Everything is great in Wonderland. But of course, this is not always the case. For example, now if we run the same query with 5 rows, notice what happens. When we go to our execution plan, he says, okay, so I estimate that I'm going to read 1 row, but he's actually reading 5 rows when you read the actual number of rows read. So this is horrible, because when you're going to plan for something, if you're always thinking that you're going to use 1 row, everything changes and you can have very bad not optimal queries, execution plans. So now let's clear again our cache. And let's change our compatibility level to 150. When we do this now, and we run this query, notice that he now is estimating, if you read the estimated number of rows to be read, is now 5. And the actual number of rows he read were 5. So of course, this is going to generate a more accurate plan. And all we needed to do, again, to take advantage of this was to change our compatibility level. Again, remember, Microsoft is trying to enhance the query engine to have the best gains with minimal impact on our side. So we don't have to change our code. We might have some legacy application that we can't touch the code, etc. And we're using table variables. Well, this is something that we can benefit from. Now, Let's see at the following scenario, because this is not all happy wonderland. Let's create a store procedure, which is going to use a table variable. Very simple again. Basically, it's going to insert from our users table into a table variable, and it's going to do some joins with other tables. So let's create that. And now we are going to change the compatibility level to 140. Let's clear our cache. And now when we execute our store procedure, he is going to estimate the query plan based on one row that he thinks that he's going to read. Again, this is because this is the way that it was done before 2019. It's going to underestimate the rows in the table, which is going to lead to single thread processing and low memory grant. So what happens is that he says, hey, I'm only going to read one row, so I'll just ask for very low memory. And then when he's actually running, he's like, oh my God, I need more space to actually run this. He is going to spill into tempdb, and it's going to cause contention in tempdb if there are other concurrency processes running, and it's going to cause a lot of pain. Notice that we've been talking and it's almost a minute and this query has not finished. So I'm going to stop it. I am going to say, hey, show me your estimated execution plan. When we go in here into the estimate what he's going to use, and we go to our user table, notice that he says the estimated number of rows to be read is 1, but we're actually reading about 8,000 rows. Okay, so let's go back to our 2019 compatibility level. We're going to clear our cache again, and now we're going to run the exact store procedure. And now what it's going to do is going to be a bit faster because it's going to accurately estimate the rows for the table variable. The memory grant is going to be more accurate, and we should have less tempdb spills. All right, but we want to note what happens with the memory grant. We mentioned that the memory grant was actually introduced in 2017, but only for batch mode. So now after 2019, the memory grant is introduced. Notice that it took 28 seconds. The other one had a minute running and it hadn't finished. When we go to our execution plan and we look for our table variable, notice that the estimated number of rows to be read is 8,704, which makes the plan way better. Now, a couple of new things in 2019 and the latest version of Management Studio. Notice that our operators here has a little circle with 2 arrows. That is telling us that our query is going into parallelism, which is a good thing that we can now identify right away without having to read every little step of our plan. And when we go to our result here, notice that in the memory grant, it has 1.6 gigs of memory that it's asking SQL for this query. So this is a lot of memory for one operation. If we right click on it and go to properties and we go to our memory grant info over here, we notice something that is new. We have something that is called is memory grant feedback adjusted. And what this is doing is telling us that this hasn't been executed before. So this is the first time that I'm running. I don't have a last request the last time you ran it. I think I want somewhere around 6 gigs of memory, but the server only gave me 1.6. This is crazy. 6 gigs of memory for this query. So if we run it again, we'll see that it's going to adapt. It's going to say, hey, last time I ran, I asked for 6 gigs of memory, but I did it with 1.6 gigs of memory. Is this the best way? Is there something I can improve? Can I adapt? So this is what adaptive memory grant feedback does. It's going to give feedback to the query optimization about previous executions. So now when we go to our execution plan and we go to our select, notice that now in memory grant, we went down to 500 megabytes of memory, all the way down from 1.6 gigabytes. If we go into the properties again and into memory grant info, notice that now the is memory grant feedback adjusted is saying, yes, I have feedback and I'm adjusting. So last time I asked for 1.6 gigs, now I want 500 megabytes. And it gave me 500 megabytes. So let's see what happens if we continue to run this same store procedure with the adjustments. So while that is running, let me go back real quick to our presentation and talk a little about memory grant feedback. Basically, the cardinality estimation underestimation issues can result in operations spilling to disk. When we ask for little memory, it can spill to disk if we need more memory. There's not enough memory. Conversely, if the cardinality estimation overestimates, then we waste memory because remember, SQL does not share. So he's going to keep the memory that he asked for and he's not going to give it back. And that can impact our workload concurrency. So intelligent query processing comes to help with this. So if we have an operation that spills to disk, then memory feedback is going to add more memory for consecutive executions. If a query operator wastes more than 50% of the memory allocated, then he's going to reduce the memory for consecutive executions. So remember we were saying that there's a feature that is telling us when it's the first execution, the second execution, when it's adjusting, etc. So basically what that is doing is saying, hey, this is the first time I'm running. If he's running for a second time, he's going to adjust. And once he finds stabilization, he's going to say that I'm stable. So let's look at that real quick. So now, if we go back to our query, now we notice that he said, oh, I granted 522 megabytes. So let's look at our properties for the memory grant info. And he said, hey, last time I asked for 522. Now I wanted 522 and I got 522. So I'm stable. So this is the optimal query plan for what I'm doing right now. So all is well in the land. But that is not true. Because one of the things that happen with SQL is that we have something called parameter sniffing. That is not the scope of this talk. We can have a separate talk just for that because that is one of the biggest headaches for performance tuning. And we're not exempt from parameter sniffing because what happens if I now run the same store procedure, but I say that my parameter is now going to be Boston instead of the United States. So when I run it, now he's going to use the plan that was already cached and that SQL says it's stable for when I say United States. So this hurts the performance when you have different parameters that you're sending, different values in the parameters that you're sending. And it's something that we have to keep in mind. This is something that actually falls upon the on the, let's say, the lap of the database administrators, because this is something that is that's out of the development scope, and it comes into handling production issues. So notice that he's saying, oh, everything is fine. I asked for 522 megabytes, et cetera, but the result set is actually a lot less than the other one. So he's using way more memory than he actually needs. Let's do this test real quick. Let's clear our cache. And now let's run it with Boston. And notice that now he's going to prepare a plan that is going to be optimized for this execution. Give it a second to finish. There we go. So now notice, and this is also one of the cool things about the new Management Studio, notice that we have a warning sign here. So when I come here and I hover over it, it says warning. The query memory grant detected excessive grants, which may impact the reliability, grant size and issue, etc., etc., etc. So now we get a warning saying, hey, something is not right here. When we go to our memory grant, notice that it asks for 441 megabytes. This is going to be our first execution, right? So we run it again. And now he's going to adjust and adapt to this specific parameter. And it should, in 1 or 2 executions, fix that warning that it was giving us, saying that something wasn't right with our memory that we're asking for our query. Let's give it a second to complete. And notice that now we don't have our warning sign. So he adapted. When we go to our memory grant, he's saying, I'm adjusting, and now I'm only asking for 13 megabytes instead of the 441. So now what happens if I run with the United States? Now, he's going to use that last catch plan with the 13 megabytes, and we should get a spill because he's not going to have enough memory to catch everything in memory for what he wants to do. So this is something, of course, that we have to keep in mind, that we do have these benefits, but they do come with a cost. And at the moment, we don't have a solution for that. We need our DBAs to be on top of these things. All right, so let's give it a sec for it to complete. Notice that it's actually taking longer than previous executions, which were around the 30 seconds mark. And now when it completes, notice that we have a warning sign here on our hash match. So it's saying, hey, operator used tempdb to spill data during execution. I had to write 22,000 pages to tempdb. Because I was only granted a specific amount of memory that it thought I needed. So this is cool, being able to see these things more easily than before. And always keep in mind, when you have performance issues in production or in your development environment, to look at your plans to see what's actually happening here and see if we can take advantage of these new features, okay? So let's carry on with our presentation here. So next we have our batch mode on row store. So batch mode on row store. This enables batch mode execution for analytical workloads without requiring column store indexes. So column store indexes were introduced in SQL Server 2012. It was intended to accelerate analytical workloads, okay? So with batch mode processing, the query operators process data more efficiently. It's designed for large sets of data. They work on a batch of rows instead of one row at a time. So we need to be careful here because we need to understand which workloads could benefit from batch mode on row store. So what happens is that we could have a database where, because of whatever nature or reason, we can't have column store indexes because they are expensive to maintain. They have specific cost on transactional systems. They cost. So we might not always want to use them. They're more for analytical things. But sometimes we need to do analytics on our transactional data store. So we could now benefit from this batch mode on our row store transactional system. So what this consists is basically 4 analytical queries. This is, again, something that is automatic, something that the engine does without intervention from us. All we need to do is make sure that we are on the compatibility level for SQL Server 2019. So we need to understand that our workload needs to be CPU bound. We need to understand that we're going to use this for CPU excessive queries. If the bottleneck is I/O, it is still recommended that you use a column store, okay? But if it's more CPU, then we can, when it's possible, not to use column store, we can benefit from this feature. So let's look at a simple example of this real quick. All right, so for this example, I am going to be using the Wide World Importer DW database, which is also a free database that's online. I am going to set my compatibility level to 150, so I am on 2019, and I'm going to clear my cache. Now, I'm going to use my database, and I have this query that I am going to set a query hint, and I am going to force it to recompile a new plan and use this allow batch mode. This way, I am forcing it not to use this new feature so that we can see the behavior. Let's include the actual execution plan and run our query. Okay, so notice that this is a very, very, very simple analytical query. We're doing some sum operations, right? Aggregation, etc. Notice that we have the following. He is doing a table scan, right? Notice that this arrow is kind of bigger than the other one, fatter. So this means that it's estimating a large amount of rows that it's reading. Notice the estimated number of rows, which is, let me see, 22 million rows he's estimating that he's going to use. But eventually at the end, he only used 202. All right. So let's now use our batch mode. Let's clear our cache. Now let's use our batch mode on row store. I am going to set the option to recompile so I can make sure that he's going to generate a new query plan, and it's going to be basically the same query. Now I'm going to run it, and notice that it ran way faster. The other one ran for about 13 seconds. This one ran for 1 second. We have the same result, and notice now that it's a little different. Now he's reading, like, all of the cost is here on this table scan heap, and he went into parallelism, so it's way faster. I do have a warning sign here saying, hey, I thought I was going to need a lot of more memory. I actually didn't. So we might want to fix that. So if we keep on running this, our adaptive memory is going to keep on making this better. So let's see if he changed here real quick. All right, so he's saying this is the first. Oh, wait, I'm sorry. If I put the recompile option, he's going to always say this is the first time that I'm running. So let's leave that out. All right, so now let's see what he says. All right, so this is the first execution. Let's run it again. Notice that now I don't have my warning anymore. And when I come here, notice that he went from about 100 megabytes to just 13 megabytes. So he's adjusting. Last time he asked for 80, now he's asking for 13, etc. So this improves the memory grant usage, the memory that it's using. It makes it faster because I am using batch mode. Instead of going one row per row, now I'm handling batches of row. We all know that batches are more efficient when we are doing CPU intensive operations. So again, we need to understand which workloads are going to benefit. This is not for every query for use. It's mainly for analytical queries that we're going to be using on top of our transactional database system. All right, let's continue now with something that we all love. Oh, wait, no, we don't love. Or we do. Let's see. So T-SQL Scalar user-defined functions inline. Queries that reference T-SQL Scalar UDFs use iterative invocation, right? So what this does is that it lacks cost. The query optimizer can't estimate what it's going to cost when you use these functions in your queries. And it's going to force a serial execution. So it's going to go in order one by one, etc. So in SQL Server 2019, now these UDFs are transformed into equivalent relational expressions that are inline into the calling query. So now often we result in a significant performance gain. So why do we love functions in SQL Server? Well, we can say that user-defined functions that are implemented in our T-SQL code and return a single data value are referred to our user-defined functions. They encapsulate code and make our code more easy to read. It makes it more elegant. It makes it better for reutilization. It makes it better to express in certain situations when we have complex business rules. And it helps with that complex logic without requiring expertise in writing very complex SQL queries if we break things down into small bits. So we love functions for that. But why do we hate functions in SQL Server? Of course, there are performance issues because the way that it is invoked, it's one by one. So we have to repeat every execution for every row in our query that is calling the function. So when the query optimizer is preparing a plan for this, he can't effectively say, hey, this is going to cost this much. So we can't create effective plans. Each statement itself is compiled, so we can't reuse the compiled plan. It's not cached. We can't take advantage of these adaptive new features that are there to make queries better every time it runs. And it doesn't allow intra-query parallelism in queries that invoke UDFs. So we can't take advantage of going multi-thread. So those things are hard, which is always why it is recommended that you only use functions when it is extremely necessary, and especially for small workloads. Of course, Microsoft comes to the rescue, and they're trying to make this better. With 2019, now these scalar UDFs are being transformed into relational expressions that we can now see in the calling query. So the goal of this is to improve the performance for queries that invoke these UDFs, where the execution of the UDF is the main bottleneck. So let's look at an example real quick. So again, we have our database, and we're going to set it into our 150 compatibility level, and we're going to free our procedure catch. So once we do that, now we are going to use our database, and we are going to create this function, which is going to categorize our customers based on the total amount. It's going to say that if it's less than 500,000, it's going to be a regular. If it's less than 1 million, it's going to be gold. And if it's anything else, it's platinum. So let's create our function. And now there is something interesting here. In order to know if a function can be inlined, we can use this system table called SQL modules, and we pass the name of our function, and we can see if this UDF is eligible for inlining. Not all functions are available for inlining, so we'll see that in the next slides. Notice over here it says is inlineable. It has a 1. Okay, so that means that this can be inlined. So now I am going to use a query hint again to disable it. I don't want to see it right now. I don't want to see what UDF inlining does. I want to see what it did before, the legacy behavior. So when I execute it, oh, and I missed the actual execution plan. Let's clear everything again. So let's go back here and run it with include, yes. All right, so when it runs, right, it gives us 403 rows. In our execution plan here, we see that it just has a cluster index scan, a top, a compute scatter, and our select. That's it. We don't see here the actual execution of the function. So now when it's inlined, we're going to force it to recompile here. So create a new plan. It's the same query, but it's not going to use the inlining feature. Notice that it gives me the 403 rows, but now the query plan is way different. We now have the actual execution, what is going on inside of that function. So when you're troubleshooting performance issues, this will give you more insight into what the function is actually costing the query that you're trying to run. This is, again, something that we can take benefit from with our compatibility level in the new 2019 version. So what are the the functions that are candidates? All right, so for this first version, and I use the term first version because this is something that they're going to build upon. In further versions of SQL that come, they will add more candidates for this feature. So right now, functions that just have a normal declare set operations, select values, if else, return, a nested recursive function call. It also can be inline, and relational operations such as exist is null. But not all can be eligible. For example, non-inlineable constructs. When we invoke a function that is dependent on getDate or has side effects such as new sequential ID, they can't be inlined. When our functions reference table variables or table value parameters, it can't be inlined. When we use another scalar UDF in its group by clause, then it can't be inlined. When we use in a computed column or a check constraint definition, then it can be inlined. Microsoft says that they have received a lot of feedback on this scenario, and they're working on that for the next version. When there are references to user-defined types, and when we use partition functions, so when we are partitioning tables and user partitioning functions, we can't take advantage of inlining. So we need to be careful here when what functions can be used to take advantage of this new feature. And the last feature that we're going to talk about in intelligent query processing is our approximate query processing. And this is very interesting. We know that when we use count distinct operations for big data scenarios involving many distinct values, the results can be very large and request a large memory grant, and that can impact your concurrency. So in SQL 2019, for scenarios where the exact values are not required, and this is important, exact values are not required, we can use approx count distinct. This is a new function that improves performance and concurrency by using a very small memory footprint. The function implementation guarantees, according to Microsoft, that the count that is going to give you will have a 2% error rate within 97% of the times that you run it. So that means that 97 times out of 100 that we run this, we're going to have a 2% error rate. All right, so this is important to know. And again, I say, this is why this can only be used for scenarios where exact values are not required. So this new function is new in 2019. It aggregates across large data sets where responsiveness, this is the key, responsiveness is more critical than the absolute precision. An example is, for example, when you're calculating a count distinct across 10 billion rows for a display on a dashboard. Now, on a dashboard that is constantly refreshing itself every 3 to 10 seconds, this can have a heavy impact on your workload. So In this case, absolute precision shouldn't be important, but responsiveness is critical. So there you can use this new function. We need to be very careful here. Again, I won't stop repeating it. No banking applications or anywhere where an exact value is required should use approx count distinct, okay? So this function is designed for use in big data scenarios. Do not use it for small data scenarios. It's not worth it. It's optimized for the following conditions: when you're going to access data sets that are millions of rows or higher, an aggregation of a column or columns that have many distinct values. So if you're using a group by and there are going to be a lot of different values, this is optimized for that. It requires less memory than an exhaustive count distinct operation. And like we mentioned, this is good for data science, big data set exploration. You need to understand the workload that you're going to employ this in. So let's look at an example real quick. And again, we're going to set our database to our new compatibility level 150. We're going to clear our cache, use our database, and we're going to include our execution plan. Now, very simple, because of timing, we're not going to run on very, very large data sets because this will never end. But let's run this here. This is using the memory hint to not use batch mode. I don't want to use batch mode because remember, batch mode is something new that is going to help in this type of situations. We talked about in batch mode on row store set. So we don't want that. We want it to be raw, the legacy effect. So notice that it gave us a value of, some commas would be great, 29 million rows. So this is our exact count, 29 million rows. And if we look at our execution plan, notice here that it's going to do its table scan and look at the memory. He said, hey, I need 1.6 gigabytes in order to complete this. All right. So then he is asking for a lot of memory because this is a count distinct. Now, let's clear everything. And now let's use our, again, we don't want to use batch mode. We don't want to take advantage of this new feature. We want to just to use the new function on the same query, just changing our database availability and compatibility level, sorry. And now when we run it, notice that the count is different. Again, it says that it's going to give us about a 2% difference error rate 97% of the time, but it's pretty close, 30 million, 29 million. And when you look at your execution plan now, notice our memory grant, 72 kilobytes, from 1.6 gigabytes to 72 kilobytes. So again, this is very interesting. It's awesome that it's available because we can take advantage of it. It just has to be in the right scenario where we want an estimate value. We don't want the exact value because I want it to be able to respond quickly for a dashboard, for a report, for data science, big data exploration, where I need to understand data distributions quickly and exact values are not paramount. So this could come very handy in using it, and it won't disrupt your normal operation workload by hitting that memory grant that's so large just to get a count. So if we continue with our presentation now, we have something very interesting here. Okay, so I think this slide is trying to tell us something. And I want to make this, emphasize on this deeply. Whenever a new version of SQL Server comes out with new features that affect the query processor, do not jump on those features on your production systems right away. Again, do not do it. Why? We need to test the living snot out of these features before we can put them in our production system. The reason for this is because we could have regression, we can have unexpected behavior in our system. So we need to make sure that what we are implementing is giving us the results that we want. I don't know how many of you remember when SQL Server 2014 came out and it implemented a new cardinality estimator, and that created a lot of problems for a lot of companies that jumped on 2014 right away without doing the appropriate testing. Queries that were running way fast in their older version were now very slow because of issues in the way that the queries were implemented and the way that the new cardinality estimator were interpreting them. So as with all new features that are implemented in new releases, you should not just hop on them and change your production servers. Test, 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 test. We need to make sure that we do not cause problems in our production system.
So, so first, I want to thank you all for taking the time to be here and listen to these talks. Hope you enjoy it and find it interesting for any purpose. So today, well, my name is Francisco Mercedes. I work as a software engineer on Untitled Partners, and today I will be talking about clean architecture and how to abstract and define the details. So we will dive into our agenda, and the first thing we're going to talk is what's not a clean architecture. We will discuss in general what makes an architecture to not be clean. Then we're going to talk about the raw materials, and we're going to take a closer look at what are the materials that allow you to make or craft a good architecture. Then we're going to talk about combining those materials and see what we get. What will be the result of the crafting? What we get after make usage of those raw materials. Then we're going to talk about the details, and we're going to watch out, because these things are the most dangerous things in your architecture. So we should keep them carefully close, because inevitable we cannot get away from them. Then we go on to have a conclusion on all the things that we talk, and finally conclude of what clean architecture is and is not. So first we're going to talk about what's not a clean architecture. So that's the architecture that, instead of exposing its intention and purpose, it better expose the frameworks and technologies that will be used. So instead of like explaining or exposing, when you dive into the architecture, what's the intention, what the system for, what you will use it for, you first or you only see that the frameworks that you're using WebSocket technologies, that you're using APIs or other frameworks. So in this example, we have an example of frameworks and tech showcasing. So we have a MVC application, and when I see that code, the first I see is that this is an application, web application, an MVC model view controller. You have controllers, mothers, scripts, but I don't see the intention of that software, of that system. And you will say, oh, that's just a brand new created project. So the second one is a project that actually has some things in there, and it's like questionnaire 2011. And the first I see is also the technology they are using. They're using AutoMapper to do some mapping. They have the controllers and models. I see the word database initializer there. So they are for sure using the database. I see the inject, a dependency injection framework for IOC, and I see they are using view models and views. And when I see it, I'm not seeing the intention. I'm not seeing what the system is for. I'm just seeing the frameworks and technologies they are using for to the system. So on the second, on the third image, we can see something acceptable to explain intention rather than technology. So when I see that project, I see that there is management, there is partnership, there is payments and social network. So I can have an idea of how this application is for, what's the intention and what's the purpose of the application. So that's what's not a clean architecture, in my opinion, is. And that opinion is based on the experience and articles, books, and talks that I have read and saw. So the raw materials are what allow us to build this a clean architecture and any architecture. And those raw materials, all the test cases, are also known as use cases or user histories. And that's the only thing we need to have to actually create a clean architecture. And we'll see what's an ideal test case. So an ideal test case are those that do not contain any technical details, but the reasoning behind them, and it's accompanied with all possible scenarios. So if you receive like a test case, that test case will not be telling you that you need to have like a website, or you have to have a mobile application, or you have to have a SQL, Microsoft SQL database, or telling you the technologies you need to use. It should only tell you the logic and the reason behind the test case, the use case, and the scenarios, signs. Okay, you need to produce invoicing. That invoicing has to be delivered to the client. If the client do not pay on time, do this, do that, and like telling the reasons, the like a normal conversation, the business reasons of the case, and all possible scenarios, not talk about technical details. That's not should not be on the test cases. So now that we got those test cases and we combine them and we use them, what we get. So what we get is abstraction. So by analyzing and studying those test cases, out of that we can build and get architectural components that fulfill their needs, like the need of the test cases, without thinking about frameworks of technology. You may be wondering, how come I will like abstract if I don't know the technology I will be using? So what you will be abstracting is actually the test cases, because the technologies that you will use are details, and we will see that later. So an example of that is like to create something called boundaries or abstraction boundaries. So in this case, we see something called like interactor, which in your architecture are the responsible or controlling the business logic. Example, you need to create an invoice for a customer. So let's say an invoice is an entity that you will represent you will represent it as an entity, and the interactor will be the service or mechanism that actually will take the information like an input and will produce an invoice as an output, right? So so instead of like defining your the technology you will be using and the things you will be using to actually perform the task, you only expose the behavior of that interactor and how it will behave in your architecture, and you will protect it with architectural boundaries, which normally are commonly known as an interfaces when you are coding. So you will abstract away the details on how those things are made, and you instead will define the boundary of the abstraction on it. So out of those test cases, we will get these architectural components. But what are those? Those are the building blocks for your architecture, and the only ones that know about each other. Commonly, they are expressed in diagrams or code, like UML diagram expressing like dependencies and entities, or code like a package that an architect also can deliver, containing all the abstraction that engineers has to implement. And this is split it like in two major groups. So we have the data and we have the business logic. So the data is what represents things in our what represent things in the use cases, as in the uh, in the in the architecture it represents like customers, like from out of the test cases it represents like customers, invoices, things that has to do with the logic, and it could be like persistent entities, so those entities that you store in a database. Also could be requests or commands and queries, if you are familiar with the parent command query responsibility. Responses or like requests as HTTP requests, that could count as a data entity. A response, like an HTTP response, or any kind of response, a model or even a view model that counts as entity, and a DTO. For the other side, we have a business logic where we what we call kind of interactors, which are the ones that control the dance of the entities. Like interactors are the one that take the entities, or could be like take a request, compute it, and deliver a response, or persist persist that information into a persistent entity. You can also use things as presenters, managers, and helpers. Commonly, I do not use those. Um, because at the end, for example, if you use that has more to do with clean code rather than clean architecture. There's a book that you guys have to read. Uh, Normally, I see in code things like date helper. But at the end, this date helpers is a service, right? Normally I split these things into things: services and providers. Providers are something that provides me something, and services are things that compute or modifies the entities. And also you can have like a combination of those kind of actor, that is programming paradigm where an entity contains its state and also contains functions that actually mutate and change the state of the entity. It's commonly used in games, that instead of like when you a player being an entity, and then if a player jump, instead of having like a separate service that actually make the player jump, they have a player as an actor, and the actor itself has a function jump, and then the actor itself changes its state, and it gets rendered. So out of those test cases, what we get are architectural components, and are these ones in here. So the combination of the data and the interactors drives into the business logic, and the business logic contains entities, abstraction, and inevitable behavior like interactors that is possible, that if possible must have the ability to be extended. It means that if you have a system, and that system, for example, has to produce an invoice, that's like most of the common things every company sells and produce invoice. That system, you will have like this invoice service as an interactor, as a service, but that invoice, you should do it in some way that can be extended following a common principle for solid, is the O, when your system has to be open to extension and closed to modifications. So you must design it in a way that people can extend that invoice processing or any process that you have. So now we're going to talk about the details and what we consider details. Everything that is not derived from the test cases and do not act as an architectural component, which are the ones that I explained early, should be considered details. So details are those things that are not part of the core or the foundation of the business logic. So when a customer comes to you and say, I want an invoice, I want an application to do invoicing, Uh, they are not telling you to do an API. They are not telling you to use a database. They are not telling you to make it as a Windows service. They're just telling you they need an invoice system. So all those things that are not part of that test case, you can consider them as a details, and you have to protect yourself. Uh, your architecture, just those architectural components from those details. Uh, so one of those details are the web. So the web, desktop applications and mobile applications are just an I/O device, and it's an I/O device to your business logic. Same as your keyboard is an I/O device to your computer and your program, or your disk is an I/O device to your data. The web is not an architectural component. So the web shall not be part of your architecture. Instead, instead of like uh, exposing, putting like, and we need to have a web application. That's a decision that should be deferred and take it later. The first thing that you must think about when you are doing your architecture is about those test cases that were delivered to you, and you have to start building upon those test cases the ability to interact with your business logic. So the way we programmers do it is by building APIs. So an API, an application program interface, it's a way where you can express your business logic, but do not define the way you access that business logic. For example, commonly I talk to people and they tell me um, they think like when that the backend, like you need to talk to the backend, you need to talk to the API, and I ask them, but how do I access that API? Oh, it's on the web. It's a link. Uh, but the API, it's only the expression of those business logic, the expression of those test cases. Now, you can create pluggable components that can grant you access to that API. For example, you can construct a web API, which is a component out of your architecture that allow you access this interactors that are services, providers, and systems. You create this web API that grant you access to that system, but also you can use other things to access. You can create a desktop application, and people can interact with your business logic without having a web API. You also can have like a common language, a CLI, common language interface, like running commands, and then that common language interface can also have access to your API. So now we have three ways that can access the API, like your business logic. So in with that, I want to say that what actually matters is that business logic and that data, and not how you access that data. And I have a picture here of a popular site, which is Amazon, where people can buy things. And Amazon has like a web page, and also has a mobile application, and also has other ways, has Alexa too. Those things are components that are not part of your architecture. The architecture of Amazon, when I go into the Amazon codes, instead of seeing web page, mobile application, Alexa applications in their code, what I want to see is uh, items, products, invoices. Those things tell me the intention and the purpose of the system, and not the technologies it uses. So, for example, when you are in your computer and you're utilizing a program, you have your keyword, and you think, well, I need the keyword because without the keyword, I cannot input information into my program. And then you think that the keyword should be part of your computer, and without the keyword, you will not be able to use your computer. And people tend to think that without a web page, and without a web API, they will not be able to access their business logic. And for that reason, they make that as a part of their architecture, and include them in their diagrams or abstraction code. But you also can use other input I/O devices to provide input to your program. You can use a microphone, and with that mic, you can talk to the computer, and the program will receive your input and will give you your output. You don't have to have like a monitor to actually receive information from your API for your business logic. Instead, you can have like a speaker, and that speaker will result as your output device. So saying that those things are replaceable things, the web also is replaceable and should not be part of your architecture. So here we have an example of a web system, and this web system is taking requests from the web and is utilizing the controllers and the models, and all those things are directly accessing those business objects. So those business objects, like you're coupling the web directly to implementations of those business objects, which make very difficult to actually track or troubleshoot issues or change your code, like upgrade or your code when you have this level of coupling. So instead of having your web directly talking to your business objects that were created out of the test cases, you should put some boundaries between those. So this business object, we will call them interactors. Again, these interactors, you can think in your mind that can be services, providers, managers in your code, like customer service or whatever. And this interactor controls and consume the entities and produce entities. And those entities are those things that were taken out from the test cases as customers, orders, and all the stuff. But instead, the delivery mechanism, the I/O device, that could be the web, could be the mobile app, could be an Alexa, Google Voice, whatever, everything can access this logic. Instead of you bind that directly to your logic, you will put an abstraction boundary that commonly are interfaces that will be the front in the architecture, and those will allow you to protect your architecture, just architectural components that are related to the test cases, out of replaceable things. So in this scenario, we have a user that go to the delivery mechanism, it do a request, and that delivery mechanism, instead of going directly to the interactor, it rely on the abstraction, which is the interface, and then that interface with some IOC allow it to locate the interactor that will be used to actually perform the task that delivery mechanism is trying to accomplish. So what happens there is that the user make a request, it goes to the interface, locate what's the interactor that actually can do the work for him. That interactor will start dancing with the entities, controlling them, changing them, mutating them, and then it produces a result model, which in our architectural components, we see that results, models, and all DTOs also are content as data. So it produces that and deliver that to the user. And here you see that the user do not talk directly to the interactor. The user talk to the delivery mechanism and then talk only to the boundary, and then out the boundary respond to the user. So that means that you're protecting your business logic with this abstraction boundaries, and the users are not directly interacting with those with that business logic that can be changed. So instead, imagine that we have customer service that read customers from a database. But then we decide that we don't want to use a database anymore. We want to use an API that will give us better information about those customers. So maybe that API is using a database as well, but for us, that's transparent. We don't have to know that there is a database. So because we put a boundary we easily can change the interactor, the service, instead of being a database customer service to be an API customer service. And that will be transparent from our code and the consumers of that code. So if we have a web API, a web page, a mobile, and Alexa, for example, we have four delivery mechanisms. We don't have to go and change the four delivery mechanism to start talking to the API rather than the database. We only have to specify in the abstraction boundary that instead of using this database service, this database interactor to actually perform the task, better go and use this API interactor. So for the four delivery mechanism, that's transparent because they only rely in abstraction. So there is a principle, an element in the solid principle. In the solid principle that is the D of the solid is dependency inversion. And that state that low-level modules should not depend on high-level modules, but should depend on abstraction. It means that nothing should depend on things concrete. Everything should depend on abstraction that is tunable and replaceable. So what we get by putting this abstraction binary is that we have a line. And that line has things that should be part of an architecture and things that should not be part of our architecture. For example, specifying the controller and the presenter, those things are for those delivery mechanism. And there are implementations of that boundary. So on our architecture, what we define is that we need a customer service. That customer service should be able to read, to obtain customers by an ID, obtain a list of customers with a specific data, or save a customer or modify the state of a customer. And that's the only thing your architecture should specify. The how those interactions are made are not part of that architecture. You only put the boundary in there, and then the engineers are the ones that implement those boundaries with what they consider is the best solution for them. So things as services, models, well, putting it in general, data and business logic are the thing that has to go in your architecture. Implementations of any kind shall not. So you draw a line there saying business logic is protected, and then the consumers of that business logic should plug into my architecture and not build around my architecture, and not build my architecture around those consumers of the architecture. So now we will discuss protocols. So a better one will come out tomorrow. So protocols change every time, and in your architecture, you better should specify the need of communication between interactors rather than stating the IPC mechanism protocol to be used. IPC stands for inter-process communication. This definitely is not an architectural component. So specifying saying we will use WebSocket, we will use a web API, we will use MQTT protocol in the system, and expressing it in your architecture, that's not a good way to go because those things get changed and improved every day. So instead of that, you should say that the order interactor, the order creation interactor, has to interact with the consumer interactor to know information, with the customer interactor to know information about a customer. You don't specify we need to build an API or we need to build a store procedure that reads information about a customer in your architecture. Of course, there should be an implementation, but that should be deferred. That should be for later when you meet with the engineers or you take the decision of what you're going to use to actually fulfill the abstraction boundaries that you build. So you specify this order ID has to communicate, these interactors has to communicate with these other interactors rather than say this API has to communicate with this API. So databases, another IO device. So that's something. So do not rely on it. So databases are amazing tools. They are not replaceable. They are useful for persisting, querying, sorting, and filtering the important architectural component, which is the data. So do not build around the database. Make the database pluggable, and also defer it because you maybe do not need it. So well, personally myself, when I start in software engineer, I grow with the idea that the database is the core component of my architecture. And I'm not saying the databases are not important. They are if you need them. So when you are building a system, you should not be thinking about what database engine or what persistent mechanism you will use. Rather than that, you should state that those entities on your test cases has to be persisted. How they are persisted is abstract for you for your architecture. There is a boundary in there, a line. My architecture says that I need to store my customers because I need to read them later for other operations. But the architecture should not say what database engine you need to use to actually persist those, to actually persist that information. So where the database and ORMs and gateways are located below the line. So you have your interactors, you have your entity gateway, which could be a repository, service, a provider. Those things are defined in your architecture, but the implementation, it's a detail. That's something for later. Uh, and uh, what I something that I want to say is that it's not that you don't need the databases. If you have, for example, a bank, well, let's say any transactional uh, application. So the data that will be persisted, you probably want that to be uh, uh, managed by a database engine that actually can fastly, very, that very fast can query them, can store the information, that can ensure the integrity of the information with the constraint, the foreign keys, the indexes, and everything. You maybe want that, but that's not something that should be thinking about when you're architecting a system. What you should be thinking about is that you have a customer service, and that customer service has to store the customer somewhere. The house, you don't have to think on the house. How that will be stored is not important when you are creating that architecture. Now, when it's the time to implement that architecture, when you define the boundary, the interface of the customer service, now then you sit with your team of engineers and discuss what will be the best solution to actually store that information. Example, very popular application that is Spotify for streaming music. So if I get to architect that application, what I will state is that I need to store the music somewhere because later I have to stream that music for people to listen that music. So I will not think the database engine that I will use to actually store the music. Then when it gets the time to implement it, I will sit with the team and see, well, we need a high throughput mechanism, IO device, to store the information and stream the information back to play on the phones. So on that time, when it's time to implement it, it's a time when you think about it, but not when you're architecting the system. Miscellaneous things. It could be everything else that is not in that business logic and that is not derivative of the use cases. So IOC algorithms, program languages, even the program languages. The decision if we will build it in Python, on C#, on JavaScript is not important when you're architecting the system. That's an implementation detail that can be deferred and take the decision when actually the decision has to be taken. If none of the if none of them express intention and purpose, saying that you will build a system on C#, do not express intention of your system, which is only which is only the only thing that is that's an architect you must dictate to the abstraction and architectural components, then we shall not consider that as an architectural component. So as an architect, you shall not dictate what programming language should be used. You only dictate the behavior that should be implemented, and and then the engineers, then, well, it's not that you shall not be part of the decision. You can be part of the decision, but the engineers, like the team, is the one that chooses the tools to be used, the details. You dictate the behavior, and the engineers and the team pick the tools that will fulfill the need of that behavior. So the conclusion is like how to identify a not clean architecture. So if the architecture dictates the technologies and frameworks to use rather than the intention and the purpose of the system, then we can say that that's not a clean architecture. If it lacks on a clear definition of the architectural components, those things that were obtained of the use cases, I think that's the raw material. That's one of the most important things, those use cases, because out of that is where you can obtain the business logic and the entities, the data that you can use, that you will need to fulfill the system needs. So if it lacks on the a definition or a clear definition of the architectural components out of the test cases, maybe that's not a clean architecture. If the details and decisions cannot be deferred or delegated to others but the architect, like if it's only the architect that has to pick the programming language, the database engine, the delivery mechanism, APIs, mobile, those things, if that's decision only for the architect and it put it into the architecture, then you are bounding your architecture to those details. And as they are details. They're not the core thing. You shall not bind those things together. So that's maybe not a clean architecture. So you have difficulties to extend or plug in and out the details. If, for example, the example that I said earlier, if you have an interactor, a consumer service that is using a database, and it's really hard for you to remove that database and switch to an APIs that the API maybe is using a database behind the scenes, but you don't care. If it's hard to do that, like if you have store procedures and then you need to use directly the store procedures, and it's not easy to switch that logic into an API, then maybe you don't have a clean architecture.